Good afternoon, everyone. My name is Joris Guérin, and today I'm going to give you a talk entitled Robust Detection of Objects Under Periodic Motion with Gaussian Process Filtering. This work was conducted at Universidade Federal do Rio Grande do Norte, which is located in Natal in northeast Brazil. Let's begin. So to begin, I'm going to give you some context to better understand the problem that we're trying to solve. So let's start with the following example. Let's say we are on a production line, an assembly line with in the automotive industry, and we want to make sure that the car is not leaving out the factory without this lead for the fuel tank. So to do this, what we can do is train an object detector to make sure to detect the object, and if when a car goes through the production line, if the detector detects it, then it's okay, and if not, we can trigger some actions because there is some issues. The problem with this is in industry it's really hard to get a lot of good quality data to train such a model, and so we often end up with imprecise models. So an example of wrong model would be if the person collecting the data is not considering any other blue objects when he builds the data set. Then, for example, whenever the model sees something blue, it will trigger as if it were the object, which is a huge problem because then probably the car will go out without its lead, even if it could have been detected with a good model. Another issue could be we can build the model with synthetic images because we might have access to the CAD model of that, but then our model will be good but not perfect. And what we want to do here is improve these models in a way that we don't need to collect more data and that we don't need to retrain anything. We have a bad model, that's okay, but we want to use some information, some patterns that we know about our process to improve the results of the model. So formally, our problem is defined as follows. So we have an imperfect object detection model, as I just showed, which is characterized by its precision recall curve. This curve is basically is a parametric curve where we consider the threshold with which we accept or refuse the boxes predicted by the model. And for one given value of this threshold, we get a point on this curve. The recall means that, for example, if you have 100 objects that you need to recognize in 100 images, and if you only find 80 objects, then you'll have a recall of 0.8. Similarly, or on the other hand, if your model is making 100 predictions and only 80 of them actually correspond to the objects that you want to detect, then your precision will be of 0.8. So the objective is basically to have a point here with recall of 1 and precision of 1, meaning that you find all your objects and none of your predictions are mistakes. And so the more you increase this threshold, the recall goes lower, but the precision goes higher. It's usually like this. It has to be like this, actually. So what we want to do here is building a filtering method that enables to improve this curve. So basically having a curve above the blue one. And to do this, we'll use some specificities of the problem. So the problem that we want to study is the one where the objects to detect are having a periodic trajectories. So let's take this example of the production line, which is one use case for this method, where basically all my objects are going to have to follow this line, and then they'll go out of the video, and then another object is going in and follow the same line with a given period. Okay. That's what we want to leverage to improve the predictions. Another use case might be you have a drone that's doing patrols with always the same path. Then all the objects it's going to observe are going to appear, the static objects basically, are going to appear following a given trajectory, and at each time the drone repeats a loop, then it's a new period, and we're going to get the same thing. And so, as I explained, the objective is to use these patterns in the trajectories to filter out basically the wrong boxes and that improve the precision recall curve. So let's get into more details now, more into the method. So the big picture first. So let's understand how this method works, what we did. So first of all, we fit a Gaussian process model to the trajectories to have a regression model that can predict the time at which a bounding box is supposed to appear, given the pixel coordinates, the x and y coordinates of the pixel. We chose a Gaussian process because it has the nice property of outputting not only the prediction but also the uncertainty in this prediction. So it can evaluate if a point, if a prediction that it outputs is good or not. For example, on this figure, we can see that for x's that we've already more or less seen in this region, the uncertainty is low, but if we have a point that we've never seen before, the uncertainty is going to be high, and we know we cannot trust this prediction. And then the process will basically just go as follows. If my prediction is too high with respect to what I've seen during training, then I will discard the bounding box. And if the time predicted is too far away from the actual time measured on the experiment, then I'll also discard my bounding box. So let's see how we can achieve this. So we'll study the following toy problem to explain the method. So that's basically the image plane, and we have an object that's having this periodic trajectory along this line, and then another object appear, and so on and so on. So the first thing we need to do is to collect data to train our Gaussian process. So to do so, we'll just run the model for a few iterations on the real system and collect all the predictions of the object detector. To do so, then we'll obviously have some noisy data that are mistakes of the model, and that's it. Then we need to process this data to obtain the Gaussian process. So the first thing we need to do is to align all these trajectories that we have recorded. So to do this, we need to basically evaluate the period of our system, or periodic system. To do this, we'll isolate the t component of the data, and we'll notice that when the object is supposed to be present, there is a higher density of points along the t component, and when the object is not in the video, the density is lower. So we can conduct density-based clustering on the t components, and that will isolate 3 groups of points with a few outliers that we can remove. Doing this, then we can take the first point of each group and do a difference to evaluate the period of the system. And with this period, we can take the modulo and align the training data, basically. The next step, we need to remove the outliers. So to do this, what we can do is density-based clustering, but now on the x, y, t data, where t is basically t modulo the period. So as we have seen several trajectories, we hope and we know that there will be more than one point for each x, y, t where actually the object was present and not in the other cases. So what we do here is running the same density-based clustering, and in this way we can isolate the outliers and obtain the clean data that we have here to train our Gaussian process. Then we can just basically train the Gaussian process. I'm not going to give a tutorial on Gaussian processes here, but the output will look something like that. So for each point in our image plane, we'll have a given prediction of time, and we'll have an evaluation of the uncertainty of the model. And as I explained before, so if we have a point here, uncertainty is going to be high, so we'll discard the point because it's going to be higher than what we've seen during training time, because no point here were seen at training. And if a point is on the line, but the time predicted is too far away, for example, we get a detection here, but we expected the object to be here, then the time is going to be wrong, and so we'll discard the point as well, because it's going to be higher than the uncertainty that the model tolerates. So let's, before showing more results, let's do a quick recap about the model, about the method. So we have a real system where object detector that's imperfect is running, and the objects to be detected are following always the same trajectory in a periodic way. So first of all, we'll just run the model on the real system for a few iterations and obtain something like this with noisy data. Then we derived an automatic method to clean this data and align them. And finally, we'll train a Gaussian process model, regression model on these points. From this, for each point in the image plane, we can evaluate the time and the uncertainty of the model. So at inference time, when we get a new prediction, we'll input this to the Gaussian process model and obtain time estimation and uncertainty estimation. And if the uncertainty is too big, we'll discard the points. And if the time doesn't correspond to the time of our experiment, we'll also discard the point. Doing this, we can improve by a lot the precision recall curve. So how do we do this? So let's say our point of functioning during training was 0.8 in recall, which means that there was all these were mistakes. So the precision was 0.9, but so we had 10% of mistakes. Using the filtering that we developed, we can remove all these mistakes, which means that the precision is getting higher for a given recall. So what this means that we can go higher in the curve, so lower the threshold, and we can, without decreasing too much our precision, so we can have basically a point of interest, a point of functioning of the system that can be close to 1 and 1, basically only detecting the objects and detecting all the objects, which is good. Then we tested our method with different kind of trajectories. So this was our type problem, but we also did this, which the straight line corresponds more or less to what's happening in the production line. And we also tried this curvish line, which would correspond to basically the drone example presented before. And we also tested our method with respect to different models, some very bad and some very good and some intermediates. This green one was the one from the type problem. And the results we obtained, so this is the average precision of the reference model without the filtering. Then average precision is basically the area under the curve of the precision recall. So what we see is if the initial model is good, let's focus here first, then our automatic cleaning method enables to improve the results with respect to the reference model. But if the initial model is too bad, then the predictions are too noisy, and we cannot train our method this way because the results are actually decreasing. But there is a solution to that, is basically we can clean manually the data before training the Gaussian process. That's not a big deal. I mean, it's inconvenient compared to automatic, but it's still just basically 5 minutes of work at most to clean 3 or 4 trajectories. And doing this, we can see that we can go from 80% quality of the model to something like 95 for all of the trajectories, which is good news. That's basically mean that the Gaussian process approach is working. So average precision is an interesting metric, but I believe this one is even more interesting, which represents the optimal point of the model. So that's basically the point where both precision and recall were higher within the line, basically the average precision of precision recall. And what we can see is that that's also the case, that we go from a model that's only 70% precise to something that's almost perfect in some cases, even with the bad models. And same conclusions regarding auto cleaning and manual cleaning. There needs to be some guarantees about minimum model requirements. So that's it for this talk. I hope you enjoyed it, and thank you all for your attention. But if you have any questions, do not hesitate to let me know. If you're watching live, just ask me after this session. And if you're watching later, you can email me or contact me through any of these medias.